Hello guys, this is a continuation of the topic on beam columns. So let's now consider a general loading case upon which the behavior of the beam column will be based. So consider the case in which the lateral loading WZ in combination with any end moments M1 and M2 constitute the primary bending moment Mi, which is a function of Z. So we are now referring to the loading condition in which there is a transverse load acting okay. There is an end moment and of course since this is a compression member, so there must be an axial load. Okay, so the primary bending moment Mi is actually triggered by the transverse loading with or without any accidental eccentricity coming from crookedness. So automatically the flexural behavior of such a beam column will be initiated by the presence of this transverse load. So the total moment Mz at a certain section from the left support, a distance of Z, is actually occurring at this juncture, wherein the moment Mz is simply the sum of the initial moment, which is the primary bending moment, plus the secondary moment, induced from the mere fact that there exists an initial deflection of the beam at this particular section, a distance of y. And this total moment is simply related to the curvature behavior, wherein we all know that the moment is actually defined in terms of the curvature phi. Okay. So where phi here is defined as your second derivative of the displacement with respect to Z. So that is the curvature, such that considering now a differential equation in this form obtained by rearranging this equation, noting that there's a change of axis initially or commonly referred to this x-axis along the longitudinal axis of the member is now considered the z-axis. And by simply dividing this equation by EI and rearranging, we yield to this equation, and differentiating it twice, we yield a fourth order differential equation. So from equation 7, this is actually in terms of the total moment. The curvature which I have defined a while ago is actually differentiated twice here, so that we can make an expression or a relation to be substituted in this working equation or working differential equation, such that these two equations here, equation 7a and 7b, will transform this equation to this equation by simple substitution. Take note that the negative sign of the moment here must be considered in such substitution. So the fourth derivative is simply the second derivative of the moment here, while the second derivative of y is simply the moment over ei here, okay? Where p over ei here is a coefficient from the differential equation. So this is simply a coefficient, and this is now the y term. Or the d squared over dz squared term. So this right hand side is simply rewritten from this original equation on top. And if we define a variable k squared equivalent to this coefficient, we can come up with a simpler equation, which is a non-homogeneous differential equation. In MZ. So the solution for a non-homogeneous differential equation is simply a combination of the solution for a homogeneous form and the solution for the particular equation on the right hand side. Okay? So this is actually the solution of this homogeneous form of the equation, wherein the right hand side is not yet considered or taken to have a value of 0, while the solution here simply is the particular solution. That captures the behavior in the same form of the right hand side of the equation. So the maximum value of mz may be found by simply differentiating with respect to z and setting to 0 to get the value of your coefficients. So equating it to 0, we can actually differentiate this with respect to z in this form, such that your remaining equation will simply be given by the first two expressions, such that the third expression here simply becomes 0, because in common situations, the solution for this particular expression is made up of a polynomial of a lower degree, such that if we differentiate it, okay, the first derivative will simply be equal to 0. So this is 0 since your fc is normally a lower polynomial, which is a linear equation. And noting that this first expression is simply equivalent to the second expression, we can come up with a tangent function simply by dividing your sine divided by cosine function of kz angle equivalent to the ratio A over B, such that if we define now the opposite side of the angle KC, which is A, and the adjacent side, which is B, will give you a correlationship on the sine and cosine function by simply using or taking note that the hypotenuse is simply a squared plus b squared. So sine kz is this value here, and cosine kz is this value here. And substitution of such values for sine and cosine will yield this equation coming from the original form of the solution of MC from the non-homogeneous working equation. So why is it that this was reduced to a two-term solution? We simply combine these two expressions because they have common denominator, so it will yield a two expression, a simpler expression than this first expression here. So take note that the above equation should be modified in case the solution for the particular right-hand side of the differential equation is no longer linear, such that the derivative will not be equivalent to 0. So just be careful of such situation. So let's make things simpler by dividing the scenario into several cases. So for case 1 scenario, the unequal end moments without transverse loading, so we remove the transverse loading. We simply account for this moment M1 and M2, which are not equal. So the moment diagram will be like this, and the second moment diagram will be, of course, a parabolic curve defining the effect of the P times Y increasing as it goes into the middle of the beam section. Recall that the non-homogeneous differential equation in equation 7 is this one, and this becomes a homogeneous equation if the right-hand side is equal to 0. And what makes it 0 is the fact that the initial moment, which is normally triggered by the transverse loading is no longer present in this case. So if we take a look now on the value of mi, the initial value here, okay, is simply defined in terms of the m1 and m2 values. If we cut a section at c distance from the left support here, your mi is simply equivalent to the initial plus a certain increase, no, due to the gradient or slope coming from the m2 over m1 values. So this is simply a formula for y is equal to a constant a times plus b times x. Okay, so this is the initial or the intercept, no, and this is now slope. Okay, this is the intercept on the vertical axis, and this is now your variable. In this case, our variable is no longer x, it is a. So if we differentiate now mi on this basis, we can get this equation such that the equation is now a homogeneous differential equation, very easy to handle. And similarly, your mj maximum in equation 9, which is this one, becomes a simple equation, which is this one. Taking note that f1 of z do not exist in this case, since there are no transverse load coming from externally applied to the beam column. So let's call this equation 10a, and since f1z, as I have said, is 0, okay, so there is no transverse loading, and the constants a and b may be evaluated from equation 8 without the term f1z. So this is now the reduced equation, since f1z, the particular solution here, is no longer, okay, existent. Hence, applying the boundary conditions in this simpler moment equation, we take note that at boundary z equals 0, your mj is simply equal to m1. Okay. And if we look into the moment equation that we have derived here, okay, so our moment equation m1, which is a function of your a plus bx here, okay, this. So we now apply again the boundary conditions wherein the value of b is equal to m1 at z equals 0. So what that means is that if we take a look at the moment, okay, considering this equation here, wherein since there is no transverse load, this is now equated simply to m1, Okay, and if I take the boundary z at 0, the sign of 0 is simply 0, and the cosine of 0 here is simply 1. Okay, so m1 now is simply a plus b, sorry, 0 plus b, such that your b becomes m1 at z equals 0. So at the other boundary, which is at z equals L, your mz is now m2. So you look at the variable used in this drawing. So at this juncture, z equals 0, m1, z equals L, m2. So the value of m2, which is also the mz at that particular location, is simply equal to a, the sign of kl, okay, plus b, which is m1, the cosine of kl, such that a can be easily determined by solving for the value of a in this particular equation. So that your mz, upon substituting the value of a, so this is now your a value and this is your b value, will yield to this equation. And again, maximizing, because we really wanted to know where the or the value, the magnitude of the maximum moment, we simply apply maximum minima technique by differentiating, and it will yield to this result for the maximum moment. Okay, so I did not put this into detail. I just want you to look into it such that upon equating the derivative to 0, the values of a, okay, this is your a, which is this one, no, and this b here, can now be determined in such a manner that upon simplification and rearrangement, your value for mz max will simply be equivalent to a certain coefficient multiplied by m2. So why did we use m2 here? We can also solve this by looking into the m1, no? But since we are interested with the maximum moment and m2 is always greater than m1, then the value you are going to use as your reference moment here must be the bigger moment, okay? As such that this is now what you call the amplification or magnification coefficient or factor in this regard, because mz is simply equivalent to m2 at a certain point. Okay, so mz is simply equal to m2 at a certain point, but the maximum, okay, so if we look into the maximum here, so there's a tendency for this to gain an additional, okay, mz max at a certain point here, such that mz max is a magnified moment greater than m2, where m2 is the bigger moment and m1 is the smaller moment. So for a case 2 with transverse loading and zero end moments, so the figure will look like this. So there are no longer end moments, but what will trigger the bending or the buckling effect will be the transverse loading and as the primary loading, okay, or initial loading in this form. Okay, so this is your primary moment. Okay, so Mi is simply equivalent to, this is actually equivalent to the reaction. Okay, and then we simply multiply it by the value of the moment arm in this regard. So it is now Z plus WZ squared over 2. So you just cut this beam here, just like you do in a beam problem, and then you get the moment there, which is Mi. So differentiating twice, take note that the above equation with respect to Z, we simply get negative W. Okay, so we're just trying to differentiate this. So if we take the derivative of this will be L over 2 plus 2WZ over 2. Okay, so if we differentiate it again, this will become 0 plus W. Okay, I'm sorry, this is negative. Okay, so this is minus Z squared. Okay, so this must be negative. So if I take the derivative of this must be negative. Okay, so that's why you have a negative sign there. So here f1z is not equal to 0, hence a particular solution in the lowest form of a polynomial, which is a line, okay, a linear polynomial, is given here to approximate the function f1z, and substituting the particular solution in equation 7c in this particular non-homogeneous differential equation, we can get this expression as your working expression. Okay? So equation 7c, if we want to look into it, you just refer to the numbering I made here so that you will not be confused. So I'm referring to this non-homogeneous equation, no? So this is our starting point here. Okay, so this is our starting point here. Okay, so if I now take the derivative of this, considering that my function is, the function that I use is this particular solution. Okay, so this is now your particular solution. Okay, we simply differentiate this twice. So what is your MZ? MZ is equivalent to this. Okay, there is no there is a moment, no, but there are no end moments here. So we simply differentiate this MZ value. This is the derivative of MZ with respect to Z squared. Okay. So if I differentiate now your MZ as a function, so take note that we are looking into a particular solution, no? So our MZ is simply equivalent to the a cosine of kz plus b cosine of kz plus f1z. So since we are only interested with this particular solution, so we ignore first the homogeneous part. So what's the derivative? The second derivative of this will simply be equal to 0. And f1z, since mz is only equivalent to this part here, so what happens is this k squared will retain, then mz will be substituted in this form. And finally, if we take a look at this expression, sorry, not that. Okay, so where's that? Um, this one here, okay, there's an f1z here, okay. So what is your f1z? It's simply, no, I'm not referring to that equation. I have to refer on the derivative, this one here. Okay, so equation 7c, which is the NHDE. Now, it's quite confusing, but take note, this is a second derivative of mi. So this must be, okay, the second derivative of mi, which is equal to a negative w there. Okay, so this is one here, this one here. So equating terms with equal order of the polynomial, so meaning to say that when you have an equation such as this, wherein there are a lot of coefficients which are unknown, we simply make use of pairing, no, those terms that have the same power or equal order, of the polynomial in Z. So this is a 0 degree polynomial in Z. So we equate C1 to negative. Okay, so k squared times C1 is equal to negative omega. So this is now C1 equals minus omega or minus W all over k squared. Now we equate the term which has a first order, or the linear term, which is C2Z. There's no linear term here, therefore it is 0. So this is k squared, C2 equals 0, therefore C2 is 0 because k cannot be 0. Okay, so C1 has a value, but C2 has no value, so we can reduce the equation simpler in this form, adding only the particular solution. So this is now your particular solution. Again, we have not yet included the homogeneous solution or the complementary solution. So applying boundary conditions now in this particular case, in order to get the coefficients a and b, we take the condition of the moment at z equals 0. At z equals 0, the moment is 0. So the sine of 0 is 0. So a times 0 plus the cosine of 0 is 1. B times 1 minus wk squared. So b can be computed simply because this is 0, equivalent to positive w over k squared. So at z equals L, this is your boundary. Your equation becomes 0, so there are no end moments. So a sine kl plus b, which is w over k squared cosine kl, minus this particular expression here, w over k squared. We can now solve for a by simply transposing and factoring out w there. We get a equals this expression. Hence, from equation 9, we have now a derived equation a while ago equivalent to this, and substituting simply the values for each individual coefficients a, taking the square root of that, so we just insert a here, taking the square, plus b, which is this, take the square, then minus outside of that squared sign of your particular solution, w over k squared. So mj max by factoring can be reduced in this form, and by simply using a trigonometric identity, so I did not place the details of this, we can come up with a second formula in terms of the magnification factor, wherein we all know that the moment, the primary moment that is induced whenever you have a a uniformly distributed load, this is always the WL squared over A. So changing into this first term here into a form of the moment, the primary moment, or MI or MO, then we simply multiply this by L squared over 8 and divide it by L squared over 8. Okay? Then the K there can be placed inside the L there, it's squared there, so you didn't change a thing. So second KL minus 1 will remain the same. So this is now your amplification factor, and this is your moment. Okay? So where this value again is the primary moment, and this is the amplification factor. So now for case 3, we have now the equal end moments without transverse load, which is a special case of the case 1 problem. We simply set your M1 and M2. Remember that M2 is always bigger than M1, but in this case we take, okay, into consideration an equal end moments M, okay, wherein M1 and M2 are equal both to M. Hence, this equation here coming from the first case. Okay, so let's take a look at the first case here. What we have derived is this one. Okay, so take a look at this. So I just rewrite that equation here and then simplify it by simply taking note, okay, that M1 over M2 is simply equal to what? If they are the same, this will be simply equal to 1. Okay? So this will be simply equal to 1. M1 over M2 is 1. Then this is M1 over M2 is 1. Okay, so 1 plus 1. So 1 here, we have a 1 here, plus 1 there becomes 2. No? So this becomes 2 times, there's no more M here. So the M here is out. No? So this is 2 times the cosine of KL over the sine of KL squared. Then factoring out 2, we get 2 times 1 minus cosine KL, and changing, okay, trigonometric identity, sine is simply equal to 1. Okay, so this is now your identity application, such that your 2 del will involve again an identity on half the cosine of half angle, or what you call the half angle formula. Okay, so the 2 there will vanish because some cancellations maybe will take effect by applying the trigonometric identity. So this will be simplified further into this equation. Hence, a simpler equation known as the second, okay, formula is derived. So this is now your amplification factor for equal end moments. And this case class is always the most conservative case, meaning to say, if you want to take a look at the scenario, no, of having an equal end moment, then you are on the safer side. The reason for that is because when you have an equal end moment, you are better assured that that your magnified secondary moment will be greater. Okay, so this your mz max will be greater than m here. Okay, but if you have an equal end moment, there's a tendency for the moment of the midspan not to exceed the value of the bigger moment. That's why assuming every time that your moments are simply equal ended in at the ends are is a safer assumption rather than assuming a value m1 increasing to m2. So there's a simplified treatment for this, no, which I already have introduced on the first part, but this is much more clearer, no. This is more clearer than the first derivation I made, but they are almost of the same nature, no. So consider a general loading condition, but this is a simplified treatment. So we will not use or shall I say this is an approximate method using simple mechanics, no? Not calculus, no, because boundary conditions are more accurate to consider when it comes to things like deriving moments, etc. No? Okay, using the area moment theorem on deflection concept, we can actually simplify things, but I will show you later that the error is not significant. So the portion of the midspan deflection, say y1 due to the secondary bending moment, equals the moment of the MEI diagram between the support and the midspan taken above the support. So if you still remember your tangential deviation, wherein if I make a tangential line at point, let's say B, I get the deflection here because this is a maximum value. So this slope is 0. So my maximum deflection here is this one here. No? So if I take the deflection. So this deflection has something to do with this tangential deviation at point, let's say this is C. Okay, so the tangential deviation at C from a line drawn tangent to point B is equal to what? The area of the moment diagram along BC multiplied by x bar B. So that is your moment area theorem. Now, if we do it on the other side, it's just the same, no? Okay. Now, look at the centroid. There's an error here in the drawing. The centroid of this, if we take this is x bar C class. Okay. C This is also CB. Okay. So if we do it here, this is now my distance from that. My moment arm x bar c will simply be equal to L over pi. So this is a sine curve. Okay, so remember that this is a sine curve. So the sine curve has distances taken as periods. That's why you have a pi there. No? Okay, so this are angular values. That's why there's an angular term in radians here. So you watch the areas, the area of a sine curve, half sine curve. Okay, so this is a half sine curve. We're only taking one half because the tangential deviation is only from B to C. Okay, so my area of a sine curve is just like the area of a parabola there, half of a parabola. So if this is my L over 2, this is my maximum height, which is the moment. Yes, the moment diagram. No, so this is the M over EI. Okay, so the M over EI is actually equivalent to the P delta O plus Y1. Okay, so P times the total deflection coming from the initial, bending brought about by the transverse loading plus the secondary deflection Y1. Okay, so this is the MEI. So my area for if this is a parabola will be a simple 2/3 of M over EI times L over 2, no? But since this is a sine curve, this 2/3 will be actually a 2 over pi, no? So a 2 over pi. It is approximately, it's smaller than 2/3. It's 2 over 3.1416, no? So this 3.1416. That's why you can say that the area here for a sine curve is a little bit less than the area for a parabolic curve. So using the area moment theorem, as I've said, this is your M over EI. This is your 2 over pi. This is the factor, no? And this your L over 2 is your length, and L over pi is your moment arm. Okay, so you just multiply that, you can get this equation here. Note that y1 is simply equal to this, and this term here, if I jumble the variables, pi squared E over L squared, this is actually 1 over P Euler or P buckling, no? So this is now P over PE. Define alpha is equal to P over PE. So we have simplified your y1 into this equation. But y1 and y1, they are the same, so we can manipulate this, factoring out y1. We will be having 1 minus alpha here on the left side, then cross multiply it, it goes down, and this is simply alpha delta O there. Hence, this is now your initial deflection or first order deflection, and this is now your magnification factor. Take note, the amplification and magnification are just the same, no? So you will notice that if moment is amplified, then the deflection is also amplified. So they just mean a thing. They are only of different dimension or physical description. So y maximum now is simply equal to delta O plus y1 at that particular point, normally at the center or almost the center. So this is now delta O plus y1, which is delta O multiplied by alpha over 1 minus alpha equals this one here. No? So if I take this as your alpha, delta O alpha, I take the LCD of this becomes delta O minus alpha delta O, am I correct? Okay, then plus alpha 1, okay, plus alpha delta O all over 1 minus alpha. Okay, so this will cancel. So this will be your uh, remaining value, no? So this becomes delta O times 1 all over 1 minus alpha. So this is consistent with the previous derivation we have derived on the first lecture. This is the one. And I told you that time that alpha is simply a P over PE or a P over P if this is an LRFD presentation. Okay? Hence, mz max is equal to MOB1, where B1 is simply CM1 minus alpha. And MC max is also equal to MO plus PY max. And equating these two expressions, okay, we can say now that MO times B1 here, which is this one, is simply equal to this one here. Okay, so where in Y max was substituted in terms of the value delta O 1 over 1 minus alpha. Hence, Cm can now be derived by some manipulations. So we have a Cm value here, which is this one. Okay, so the formula for Cm, which is this one, is actually tabulated on some tables. And if you take note, this value here is simply a psi value, again another coefficient defined on the basis of the parameters involved, the moment and the flexural rigidity involved. No? Note that this is applicable for usual cases of single curvature only. Take note, when you use this into a double curvature, some values may be unreliable. Okay, and these are the suggested values for Cm for situations with no joint translation, meaning say that this is a brace column or a brace frame. And from 1 to 3, notice that these are all what? Single curvature, and the rest here are double curvature. So if you want to try using this equation, it will perhaps fall into a more accurate comparison on 1, 2, and 3, but on this, it may not. Okay? The reason for that is because of the change in curvature, there are some misbehavior on the use of the equation. So there's also a simple approximation for Cm simplified by some proponents, and this is the one that is used by AISC, and I will show you how simple it is, but it will capture some degree of accuracy comparing it with this formula here. Okay, but I'm going to stop my lecture at this point. I will continue the comparison between this method that I presented today and the AISC method in the next video. Thank you very much for listening.